Welcome to this lesson on dielectrophoresis in microchannels. Today we're going to explore how we can manipulate particles, cells, and droplets using non-uniform electric fields. Let's start by understanding what dielectrophoresis actually is. Dielectrophoresis, often abbreviated as DEP, is a phenomenon where particles experience a force in a non-uniform electric field. Here's a critical distinction. Dielectrophoresis is fundamentally different from electrophoresis. This difference is crucial to understanding the physics. Electrophoresis requires the particle to have a net electrical charge. Charged particles move in a uniform electric field toward the electrode of opposite polarity. Dielectrophoresis, on the other hand, works even on electrically neutral particles. It doesn't require any net charge at all. This is remarkable and counterintuitive. So you might be asking, how can a neutral particle with zero net charge experience a force from an electric field? This seems to violate what we know about electrostatics. The answer lies in induced polarization. When you place any material in an electric field, even if it has no net charge, the charges inside that material can redistribute. Imagine a neutral particle before we apply any electric field. It has equal numbers of positive and negative charges distributed uniformly throughout its volume. Now, when we apply an external electric field, the positive charges get pulled slightly in one direction and the negative charges get pulled in the opposite direction. The particle develops an induced dipole moment. The particle becomes polarized. It's still electrically neutral overall, but now it has a positive side and a negative side. This induced dipole is the key to dielectrophoresis. Now here's the crucial part. Why do we need a non-uniform electric field? Why won't a uniform field work? In a uniform electric field, the field strength is the same everywhere. The positive end of our induced dipole experiences a force in one direction, and the negative end experiences an equal force in the opposite direction. These forces cancel out perfectly. In a uniform field, there is no net force on the dipole. The particle might rotate to align with the field, but it won't translate or move from one location to another. But in a non-uniform field, the field strength varies from point to point. Now, one end of the dipole experiences a stronger force than the other end. There's a net force, and the particle moves. The key insight is that the gradient of the electric field squared creates a net force. The particle moves toward regions of higher or lower field strength depending on its polarizability. Let's write down the mathematical expression for the dielectrophoretic force. This is the fundamental equation that governs everything we do with DEP. The DEP force equals 2 pi r cubed times epsilon m times the real part of k omega times the gradient of E squared. Let me explain what each of these terms means physically. R is the particle radius. Notice it's cubed, so the force scales very strongly with particle size. Epsilon m is the electrical permittivity of the surrounding medium, usually water or buffer solution in biological applications. Nabla E squared is the gradient of the electric field intensity. This captures how quickly the field strength changes in space. K omega is called the Clausius-Mossotti factor. This is the most important term because it determines the direction and magnitude of the force. The Clausius-Mossotti factor deserves special attention because it encodes all the information about the particle's polarizability relative to the medium. K omega equals epsilon p star minus epsilon m star divided by epsilon p star plus 2 epsilon m star. The star superscripts indicate these are complex permittivities, which account for both polarization and conductivity effects. The Clausius-Mossotti factor can range from -1/2 to +1. This range is crucial for understanding particle behavior. Now let's discuss the two types of dielectrophoretic behavior, positive DEP and negative DEP. When K is greater than 0, we have positive DEP. This occurs when the particle is more polarizable than the surrounding medium. In positive DEP, particles are attracted to regions of high electric field strength. They move toward the electrodes or toward sharp electrode edges where the field is strongest. When K is less than 0, we have negative DEP. This occurs when the surrounding medium is more polarizable than the particle. In negative DEP, particles are repelled from regions of high field strength. They move away from electrodes toward regions where the field is weaker. Let's do a quick back-of-the-envelope calculation to get a feel for the magnitude of DEP forces. Let's consider a biological cell with a diameter of 10 micrometers, which is typical for many mammalian cells. The radius is 5 times 10 to the negative 6th meters. The permittivity of water is about 80 times the permittivity of free space, which is 8.85 times 10 to the negative 12 farads per meter. Let's assume the Clausius-Mossotti factor is about 0.5, which is reasonable for positive DEP. For a typical microelectrode array with 10 volts applied over micrometer scale gaps, the gradient of E squared is approximately 10 to the 14th volts squared per meter cubed. Plugging all these values into our DEP force equation, we get 2 pi times 5 times 10 to the negative 6th cubed times 7 times 10 to the negative 10 times 0.5 times 10 to the 14th. This works out to approximately 3 times 10 to the negative 11th newtons, or about 30 piconewtons. Is this a large or small force? Let's compare it to other forces that act on cells in microfluidic devices. Gravitational force on a 10 micrometer cell is about 10 to the negative 14th newtons, so DEP is about 1,000 times stronger than gravity. The Stokes drag force is 6 pi mu RV, where mu is viscosity and v is velocity. If we balance DEP force with drag, we get a terminal velocity of about 10 micrometers per second, which is quite reasonable for cell manipulation. Now let's talk about something really powerful, the frequency dependence of dielectrophoresis. The Clausius-Mossotti factor depends on the frequency of the applied electric field. At different frequencies, we're probing different physical processes in the particle. This gives us frequency-selective manipulation. At low frequencies, below about 1 kilohertz, the conductivity of the particle and medium dominate. Ions have time to migrate. At high frequencies, above about 10 megahertz, the permittivity dominates. Ions can't keep up, but electronic and atomic polarization still occurs. Here's a typical plot of a Clausius-Mossotti factor versus frequency. Notice how it transitions from positive to negative. The crossover frequency is where k equals 0. You might be wondering, why is this frequency dependence so useful for practical applications? The answer is that different cell types have different crossover frequencies. Cancer cells have different electrical properties than healthy cells. Bacteria differ from mammalian cells. By simply changing the frequency of our applied electric field, we can make one cell type experience positive DEP, while another experiences negative DEP. This enables label-free cell sorting. Now let's talk about how we implement dielectrophoresis in microfluidic channels. The design of the electrodes is crucial. There are 2 main electrode configurations used in microfluidic DEP, planar electrodes and 3-dimensional electrodes. Planar interdigitated electrodes are deposited on the bottom of the channel. They create a non-uniform field that extends into the fluid. Particles experiencing negative DEP are levitated away from the electrodes. The advantage of planar electrodes is that they're relatively easy to fabricate using standard photolithography techniques. The challenge is that the electric field decays exponentially with distance from the electrodes. The DEP force is weak, far from the electrode plane. 3-dimensional electrode structures, like this constriction geometry, create strong field gradients throughout the channel height. This is much more effective for particle trapping. Dielectrophoresis has found numerous applications in cell biology and biotechnology. Let me highlight a few important ones. First is cell separation and sorting. We can separate cancer cells from blood cells, or separate stem cells at different differentiation stages. Second is single-cell trapping for analysis. We can trap individual cells at specific locations and then measure their properties or apply treatments. Third is rapid cell viability assessment. Dead cells have different electrical properties than live cells due to membrane damage. Fourth is droplet manipulation in digital microfluidics. We can move, merge, and split droplets containing different reagents. Let me give you a concrete example of cancer cell separation using DEP. The problem is detecting circulating tumor cells in blood samples from cancer patients. These cells are extremely rare, maybe 1 cancer cell per billion blood cells. The solution is to use the frequency-dependent response. Cancer cells typically have different membrane properties and higher cytoplasm conductivity than normal blood cells. At a frequency around 50 kHz, cancer cells experience positive DEP and are attracted to electrode edges. At the same frequency, normal blood cells experience negative DEP and are repelled. This allows spatial separation. Modern DEP devices can achieve capture efficiencies greater than 90% for rare cancer cells. Now let's discuss droplet dielectrophoresis, which is particularly interesting for digital microfluidics applications. Droplets of one fluid suspended in another immiscible fluid act as deformable dielectric objects. They can be manipulated just like solid particles. An aqueous droplet in oil becomes polarized in an electric field. The ions inside redistribute, creating an effective dipole. Using DEP, we can move droplets along predefined paths, merge two droplets together to mix reagents, or split one droplet into smaller daughter droplets. This enables programmable microchemistry, where we can perform complex sequences of chemical reactions in picoliter or nanoliter volumes. Beyond just manipulating particles, DEP can be used as an analytical technique to characterize particle properties. By measuring the crossover frequency where particles switch from positive to negative DEP, we can determine their electrical properties. The crossover frequency depends on both the conductivity sigma and permittivity epsilon of the particle and medium. This complex equation relates the crossover frequency to material properties. Different cell states have different DEP signatures. Apoptotic cells differ from healthy cells. Activated immune cells differ from resting cells. Let's do another quick calculation to understand power dissipation in DEP devices. This is important for avoiding heating effects. When we apply alternating electric fields, we dissipate power due to ionic conduction in the buffer. How much heat does this generate? The power dissipated per unit volume is sigma E squared, where sigma is conductivity and E is electric field strength. For typical conditions, the field is about 10 to the 5th volts per meter, and buffer conductivity is about 0.01 Siemens per meter. This gives a power density of about 10 to the 8th watts per cubic meter, or 100 milliwatts per milliliter. 100 milliwatts per milliliter can cause significant temperature rise in a microfluidic device if we're not careful about thermal management. The solution is to operate at higher frequencies, where we can use lower voltages, or to use pulsed fields instead of continuous application. There's a related phenomenon called AC electroosmosis that often occurs alongside dielectrophoresis. Understanding this is important for device design. When we apply AC fields to electrodes in an electrolyte, we induce fluid flow near the electrode surface. This is caused by interactions between the field and the induced double layer. This creates microvortices that can actually be useful for enhancing mixing, but can also interfere with DEP manipulation if not controlled. The key point is that AC electroosmosis scales differently with frequency than DEP. At low frequencies, electroosmosis dominates, while at high frequencies, DEP dominates. Let me share some practical design considerations when building DEP microfluidic devices. First, electrode spacing should typically be 10 to 100 micrometers. Smaller gaps give stronger fields, but are harder to fabricate. Second, applied voltages are usually 1 to 10 volts peak to peak. Higher voltages risk electrolysis and bubble formation. Third, frequency range is typically 1 kHz to 10 MHz, chosen based on your particle crossover frequency. Fourth, buffer conductivity should be between 0.001 and 0.1 Siemens per meter. Too high causes excessive heating, too low reduces particle viability. How does dielectrophoresis compare with other particle manipulation techniques? Let's put this in context. Optical tweezers provide extremely high precision for single particle manipulation, but have very low throughput and require expensive laser systems. Magnetic separation is simple and scalable, but typically requires magnetic labeling of your target particles. Acoustic manipulation is very gentle on cells, but provides limited selectivity between different cell types. Dielectrophoresis offers label-free operation, good selectivity based on intrinsic properties, and reasonable scalability. The downsides are complexity and potential heating issues. Let me conclude by discussing some future directions and remaining challenges in DEP research. First challenge is better understanding cell-to-cell heterogeneity. Even genetically identical cells can have different DEP responses due to cell cycle stage or metabolic state. Second is integration with other on-chip techniques, combining DEP with on-chip PCR, cell culture, or mass spectrometry. Third is clinical translation, moving from laboratory demonstrations to clinical diagnostic devices that can handle real patient samples. An exciting opportunity is using machine learning to optimize DEP protocols and predict optimal frequencies for new cell types. Let me summarize the key concepts we've covered in this comprehensive overview of dielectrophoresis. First, dielectrophoresis works on neutral particles through induced polarization. You don't need charged particles. Second, non-uniform electric fields are absolutely essential. Uniform fields produce no translational force. Third, the Clausius-Mossotti factor determines whether you get positive or negative DEP. Fourth, frequency dependence is what makes DEP so powerful for selective particle manipulation. Fifth, applications span from fundamental cell biology to practical diagnostic devices to programmable microchemistry. Sixth, practical device design requires careful balancing of DEP forces, electro-osmotic flows, heating, and other physical effects.